This is page 4 of the cross-section notes, so without further ado, I guess we'll just get started. Um, Overall, if you guys get a chance to go online, ask questions, let me know kind of what you need so we can kind of get all that stuff taken care of. Okay? So once again, we're going to talk about volume of cross-sections. Um, and so again, we first have to kind of establish our base. So before we do that though, let's just kind of read through the questions. The volume of solid base was bounded by these curves, so this curve and this line, with the indicated cross-section perpendicular to the x-axis. So the perpendicular to the x-axis gives us clues as to how to set up our integral so that we don't have to get too bogged down. So we know that with the x-axis, our integral will be x equals to x equals. This will be some kind of area formula, and then this will be a dx. Okay, and our equations, when we set up our equations, the ones we use to figure out what s is, will always be y equals. Okay, so that, what we're going to have here when we do squares is, well, let's see. We know that our cross section will look something like this. So here is S, right? And so we have S. And so to make our cross section, what we're going to do is first of all establish what is the area of a square in terms of S. So our square will look something like this. So here's a square growing out. Okay, the bottom part will be S. Okay, because that's the part that touches the ground. See how it's perpendicular to the x-axis. Once you guys have that, the area will be equal to s squared. Okay? Now, what is s squared? Well, the reason why I drew this visual here is to allow you to see what was on top, what was on bottom. Because all you have to do is go top minus bottom. Okay, so again, all of this stuff depends on the previous lesson, the area between two curves. So if you haven't done that yet, or you have questions on that, you got to get that stuff squared away, then come back to this. So area equals s squared. We're going to have an integral now. We can set it up. Now that we know the area, okay, we're going to put it into our area formula. Our area formula times dx with these two integrals. So we're going to do an integral like this. We have x equals to x equals. So this will be from -1 to 3. And all we have to do now is put in our area formula. Okay, so area formula will be s squared dx. Okay, all right. So now the problem is obviously we can't, s is an x, and we have to kind of translate this. What does this mean? So at this point, what we're going to do is we're going to replace this now with the actual what s is equal to. So in this case, s is equal to top, which is the x. So I'll put in parentheses, minus the bottom equation, which is the parabola. So this would be x squared minus x minus 3. Okay? So in this particular case, let's see, we'll do a little bracket maybe just to kind of clarify things. X minus x squared minus x minus 3. Close my bracket, squared. So this is the area squared, or sorry, this is s squared, which is the area of one square. Dx gives it a little bit of thickness, okay? So it has volume now, and then we add up all of the pieces from -1 to 3, okay? And then you get your volume. All right, moving on to equilateral triangles. Okay, so equilateral triangles. Let's do some of those. Let's see, our shape will be a triangle. If you guys recall, this right here will be S. And going back, if you go back to the first page, that's where these formulas will come into play here. Our area formula, you can either derive it in terms of S on your own, or you could use the area formulas that we did in the first page, where it's square root 3 over 4 S squared. So that's the area formula. We already know what S is, okay? So again, it's going to be something like square root 3 over 4 from x equals -1 to x equals 3, and then it'll be the same thing again. X minus x squared minus x minus 3 squared dx. Again, this is the area, little bit of width to give it volume, and then you add up all the volumes from -1 to 3, all the slices to make your loaf, okay, of a triangular piece of bread, I suppose. So anyway, you got all this. Now you're going to notice that everything always has like this s squared because it's area. The only difference is this number, this coefficient in front that's a modifier. So that's why we did the first page, just to kind of show you that the pattern is always s squared. The number in front is just for the different kinds of shapes, right? I think semicircle is like 1/8, pi, right? Equilateral triangles, square root 3/4, that kind of stuff. All right, so let's kind of finish this off. So once you understand that, then the process becomes pretty easy. Okay, so let's try this one now with semicircles. Okay, let's see. Let's move it up a little bit. Okay, so semicircles. Let's draw our semicircle. We're gonna draw it kind of like this. Okay, this is the stuff that's growing out. And remember, this is S, which is the bottom. Now, I could use the formula if I wanted to from the first page. But if you aren't, like, let's say on a test, you're starting to freak out, like, oh, I forgot the formulas, it's too much to memorize, then just derive it. So I know that a formula for a semicircle, the area is 1/2 pi r squared. And we know that the radius is half of this s. So it's going to be 1/2 pi. And now we're going to replace r with 1/2 s, because that's what the radius is. It's half of this s. S is the diameter. And so we do that. So remember to use parentheses because you got to square the 1/2 as well. So once you do all of that, okay, what happens when you do all of that? You'll get area is equal to 1/2 pi, and then this squared will be 1/4 s squared, which gives you our formula from the very beginning, 1/8 pi s squared. You could put pi over the 8 and all that kind of stuff. I just like to keep everything separate so it's easier to cancel if I need to, all of that kind of stuff. Anyway, so now you have your area formula, and this problem is practically done. Okay, you know your integral goes from x equals -1 to x equals 3. Again, all you got to do is put that area formula in there. 1/8 pi and was it x minus x squared minus x minus 3 squared. Don't forget that squared. And then dx. Okay, so just remember this distance right here, this part right here, this is s. Okay, this whole thing here is the area of a cross section. Okay, all right, last example. You guys can kind of probably figure this one out. Isosceles right triangles. So again, depending on what version we want to do, there's two different types of right triangles. So go back to that first page and see. There's one where the triangle looked like this, and then there's one where the triangle looked like that. Okay, so for this one, we're just going to kind of cut to the chase. We already know the area formulas first, so we're just going to use it. So it'll be from x equals -1 to x equals 3 thing. And then the area is going to be, what was it, 1/2 base times height. So this will be s squared minus x squared minus x minus 3 squared dx. Okay, and then for this one where the hypotenuse of the isosceles triangle is the base, is s, then the equation is a little bit different. X equals -1 to x equals 4. If I recall, I think it's like 1/4 s squared. So remember, s is x minus x squared minus x minus 3 squared. Oops. Bracket squared. Very important. Okay, so there you go. All right, so hopefully that helps. We'll, again, email me with your questions, and we'll try to set up some times to meet. Okay? All right, bye.